substitution? Sure. What's going to be our u then? Okay. So du dx then is going to be 2x plus 4. I don't have an x or a 4 as a leftover there. That's kind of a problem, right? This is a u sub problem, but we have to do a little bit of massaging before we go. The trick is when you see something where you have like a 1 over and then we have a polynomial, specifically a quadratic, is what we're going to be using is this rule. So what's the integral of 1 over x squared dx? Or 1 plus x squared dx? That's tan inverse, right? So that's the goal here, is we're going to do a u substitution so that we can get it to look like the antiderivative for tan inverse. How am I going to do that with x squared plus 4x plus 5? The skill you're searching for is an Algebra 2 skill. And it's a skill that hasn't come up a long time. It has to do with quadratics. How do we take something that looks like this and rewrite it so that it looks something like this? What was the process that we used to do that? It is completing the square. That's correct. Good memory. All right, who remembers how to do completing the square? Okay, so great. So we don't have two sides because it's not an equation right here, but you're dead on. So what we'll do is we'll add the b over 2 squared, and then we'll just subtract it right afterwards, which is like doing nothing at all, right? Everybody's cool? What I'm going to do then is I'm going to group that stuff together. Because how does x squared plus 4x plus 4 over 2 squared factor? X plus 4 over 2 squared, right? Has to factor that way. We made sure it factors that way because it's a completing the square problem. 4 over 2 is just 2. 2 squared is 4, so 5 minus 4 is just 1. So we can say that, right? Oops, not x squared plus 2, dum-dum, just x plus 2. I had it right on the one before. Now, hopefully you can see that we are in the form of the antiderivative for tan inverse, right? Or that I should say the derivative of tan inverse. So we do need to make a u substitution. What will our u be in this case? X plus 2. Yeah. Which is great because du dx is just going to be 1 So du is just going to equal dx. And now if we use our antiderivative, it's going to be tan inverse of u plus c. And we'll just plug in for u. There we go. Is everybody okay with what we did there? Now, the hardest part is recognizing, like, oh, this is what I need to do in this problem. The completing the square part, dusting that off took a minute, right? We didn't remember initially what to do that, but it slowly came back. The actual process isn't that bad, right? And it's worth pointing out to you guys here that this, like Mr. Kulik can do in his head, all he's going to do is go, okay, b over 2 squared is 4. So I'm just going to rewrite 5 as 4 plus 1. And then kind of done. So, like, don't be afraid to just kind of like take that constant term at the end. You know, if it's going to like fit into the tan inverse form, you have to have plus 1 at the end. You could almost just use that as kind of like a shortcut and just be like, okay, I'm just going to write it as constant plus, you know, like break it up into something plus 1 and then just see what I can factor with it. And you probably get what you need, right? Since you don't have a lot of flexibility on a problem like this, it really has to be completing the square bust kind of thing. Okay, let's do another practice. That's smaller than I wanted it to be. So let's say, we're looking for the antiderivative of this. Try it. Separate sheet of paper, scrap, notebook, one note. Think about it in your head for a minute. See if you can get this to work out. We'll run through it together and just, you know, I'll give you a couple, 2, 3, 4 minutes here to think about it. Try to write something down. Even if you don't finish when I say time's up, that's okay. But it's helpful to kind of sit through and kind of work through some of the details on your own here. Yes. 1 over x squared minus 2x plus 2. All right, should we do this thing? So I broke that up into x squared minus 2x plus 1 plus 1. That first trinomial factors to x squared or x minus 1 squared plus 1. So we're basically doing the integral of 1 plus x minus 1 squared dx. So it's a u substitution problem. The u is going to be x minus 1. Du is just going to end up equaling dx. So this is going to be like tan inverse u or tan inverse x minus 1. Now, where on the AP exam is a question like questions like this most likely to pop up? The multiple choice question, right? It reeks of a multiple choice question. There's nothing more involved with it than just like do an integral or whatever. So like for this first one, these were from the MyAP site. These were the 3 or the 4 choices that were set with it. Do you really need to do the integral to answer this question if you recognize what's going on? No, it's got to be A, right? It's the only one it can be. Because I know I'm going to have to shove this into like that form of arctan. It's the only one with an arctan in it. I don't actually need to do the integral. I don't actually need to do the u substitution. I don't actually need to do the completing the square. I just needed to recognize like what was going on here. And then the multiple choice, because it's multiple choice, I can just figure it out immediately just because of the form, right? And on the AP exam where you have, you know, like 60 minutes to do 45 questions, or no, it's, what is it? It's 30 questions, I think. I had it just a second ago. Yeah, 30 questions in 60 minutes, no calculator. Doing something like that where you recognize like, hey, I see what's going on here. I don't actually need to do the integral. I can tell from the set of answers which one it has to be. Is enormous, like that's an enormously helpful like observation or whatever, right? If I had looked at the second one that we just did together, again, these were the list of answers given with it. Again, super obvious which one it has to be once you recognize what was going on here. Arctan's the only one that's in the form that I can have this in, right? That's it. It's only one choice. So it's not so bad. Let's do another that the technique's going to be, again, something totally doable with the tools that we have, but it's a different trick. What if we're asked to do this integral? Ideas. As it's currently written, can you do anything with this? No, right? Because you have the quotient of two functions. We don't know how to integrate the quotient of two functions. So what do I do? Well, one hope is maybe if I factor the numerator, I could reduce this down and it might just work out. I'm going to tell you right now that that's not what's going to happen. 6x squared, so 6 times 25 is, or negative 25 is negative 150. Are there two numbers that multiply to give you negative 150 and add to give you negative 4? I don't think so. I don't think so. I don't think that's factorable. What else could we do? The answer is algebra 2 again. What? Do you have an idea, Mia? Go ahead. Take a risk. The quadratic formula is not going to be what we need, although you're thinking in the right area. What type of function is this that we're doing the integral of? Where you have a polynomial divided by another polynomial. It's a rational function, right? Was there another way that I can write a rational function? So if you have some rational function, I'm going to call these f and g. You can always write that as a quotient plus remainder over divisor. How do I get it to look like quotient plus remainder over divisor? Polynomial division. Excellent. Yes. All right. So how would I do polynomial division for 6x squared minus 4x minus 25 divided by x minus 2? Can you do the shortcut, or do you have to do the long, full form long division? Can you use synthetic division to shortcut this, or do you have to use the full scale long division? This one you can use synthetic division to shortcut this. Long division would still work, but I would prefer not to have to do that. What I'm looking for to tell is the divisor. If that's degree 1 with a leading coefficient of 1, synthetic division is available to us as an option. So let's do that. If you'd like afterwards, we can run through the long division algorithm also if you think that you want to see that also. So synthetic division, we set up our synthetic division bar. What goes on the outside? What number do we write out here? Okay, it's related to x minus 2, but we don't write x minus 2 out there. Not negative 2, positive 2. So you set x minus 2 equal to 0, and you put the number out front. And then what numbers go on the inside here? Yep, 6, negative 4, negative 25. So they're the coefficients from the polynomial. What do you have to be careful about when you're writing those in? Excellent. Yeah, so if it skips a term, make sure you include a 0 there. Okay, so that's the setup. What's the first step? Yeah, excellent. You bring down the 6. 6 times 2 is 12, and we put that underneath the negative 4, and then we add down. So that gives us 8. We add down, gives us a negative 9. So what do those numbers at the end tell us? So you start at the far right. The negative 9 is the remainder. The next is the degree 0 term, so the constant term. The next is the degree 1 term or coefficient. And you just kind of, starting from right, it goes remainder, degree 0, degree 1, degree 2, etc. So what can we say then about 6x squared minus 4x minus 25 divided by x minus 2? Well, it's equal to our quotient, 6x plus 8, and then minus the remainder over the divisor. Does that ring some bells? So I can rewrite my integral as this, which is lovely because the integral distributes. And now we're in a much better place. So the integral of x is just going to be x squared over 2. The integral of dx is just x. And how do I do the integral of 1 over x minus 2? Okay, make a u sub, sure. U is x minus 2. Good. So du is just going to equal dx then, right? Hi, Blake.
Morning.
So we have the integral then of just 1 over u du, which is natural log of absolute value u, and our u in this case is x minus 2. And then we have our plus c at the end. And yeah, there's some reducing and stuff that we can do along the way, but good enough, right? So again, this would be a likely be a multiple choice kind of question. So if we look at the options, if you recognize that we're going to have to do polynomial division, anytime you have to do that polynomial division trick, you're always going to have some piece like this at the end. So I'm looking right away, and I can eliminate B and D immediately because they don't have a natural log in them. And then look at the choices for A and C. Well, C is clearly nonsense because you have the natural log multiplying to the whole polynomial, right? When I do one of these synthetic division problems, it's only going to be one term with a natural log in it. So without even doing any calculus, just recognizing what has to happen in this problem, I can answer this multiple choice question without actually having to do the calculus. Because when you're looking at 2 minutes of problem and no calculator to help you, there's almost always going to be a way to, like, just kind of, if you recognize what's going on, to answer the question without actually having to do all of the calculus. Now remember, like, if you remember on the, I posted this stuff on the web page or the site a while back. So like 59 out of 108 is still a 4. Even worst case scenario on like the multiple choice, if you just go slow and do half of it, but it's like, I'm going to do this carefully and try to make sure I get half of them right, you're in real good shape, right? If you do half correct on 3 sections of the test and then do 2/3 of them right on another, you're in 4 land. So like, you know, or you do half of them, you go real slow, do half of them right, and then you just guess the rest of them and hope to like edge up a little bit over half. You're in good shape. Like that's good. Okay? Again, I'm going to try to do, as we're getting closer to the end of the semester, I'm going to try to go back and just remind you a little bit more often here and there about like what the exam's going to feel like, and, you know, remind us about, you know, it's not going to feel great taking it. It's going to be like, oh, I'm just failing the heck out of this. And you should be doing good then. You're doing good if you feel like you're failing. You still could be doing 3s and 4s work, which is great. You know, you don't have to be getting like a 70 to be getting a 3. A 70 is a 5. And most of us that are used to getting A's on things, a 70 is going to feel like an F. You know? So don't panic. So here's another one, just for the sake of argument. I'll put this in here also. Can anybody do this without having to do the calculus? Mr. Kulik can. It is possible to do this without doing any of the calculus if you're looking at the right thing. Now, this is fundamentally more difficult than the previous one because it's a definite integral, so the answer is purely numeric. Also makes it more time-consuming to do it by hand in a time setting. So let's explain how we can do this. The answer to this is going to have a term that has the natural log of x plus 2 in it, right? Somewhere in that answer, we're going to have a term that has that. Since the denominator is x plus 2, everybody's okay with that? If I evaluate that at 2, and then I'm going to have to subtract evaluating it at 1. So my answer has to have an ln of 4/3 in it. A is the only one. Again, this is one where it's a multiple choice question. I can look at this without having to do any of the calculus and come up with the answer. As things get closer to the test, we'll do more of this kind of thing of like, let's talk through how to do one of these without, like we'll do it blunt, brute force and like do the problem. And then we'll also talk about like, hey, realistically, you can't do 30 of these problems brute force in 60 minutes. Like it's just not feasible. When can I recognize like a problem that can just look at it and figure it, like figure the answer out from the choices and save myself some minutes, And this is an example of one where, because I know what the answer is going to end up looking like, I can see which one of the solutions is the only one that has the part of the answer that I know has to be there. Does that make sense? Sneaky stuff, guys. All right. Let's do like one more of these. That's the same kind of thing that we've been doing. It's a little bit different, but it's the same kind of idea. So I'll give you the choices also. I think this one's tougher, though, to see a way to the answer without actually having to do some of it. Can we eliminate it down to any of these that are patently wrong right off the bat? Which one of these is not like the others? A, yeah. No way it can be A, right? Immediately we can say that, because I know that, like, at minimum there's like should be some kind of U substitution going on, and all they did was like drop the square root out of the denominator and multiplied it by 2. Like, yes, that's how you do like the antiderivative of 1 over the square root of x, but like, what about all this stuff under there? They didn't touch it. So immediately I know that, okay, so sine inverse is going to be the form that I have to run it into. Do you remember what the antiderivative for sine inverse looks like? Tangent is 1 over 1 plus x squared. Sine inverse is 1 over the square root of 1 minus x squared. I know, they're brutal. Again, we made go back to the Quizlet or whatever. I guess I could probably relink that from first semester. But that's the piece that we're going to have to go into. So knowing that, I'm going to have let's see, what's the best way to think about this? Okay, so 4 divided by 2 is 2 squared. So I'm going to have like 8 plus 4 minus x squared plus 4x. So that's 8 minus x squared plus 4x minus 4. Uh-oh. That's not quite right then, right? So really I should think about 12 as 16 minus 4. So when I do my completing the square, so c is now gone because I don't have x plus, I need that x minus 2 in there, not x plus 2. Is everybody okay? So this is going to be 8, 1 over square root of 16 minus x plus 2 squared. That didn't work out the way I thought it was going to. Okay. Yeah, I can. Okay, I see it. This is brutal. Get ready. So I'm going to factor out a 16 from this. Now the square root of 16 is just 4. So that's going to become a 4 out front for me. Oh, I'm sorry. 2 out front. And then I need to rewrite this chunk as that.
Why over 4? Why not like over 16?
Because I put it inside the squared. Right there, yeah. The 16 is outside the squared.
Yeah, that's smart.
Yeah, and now I can do my u sub. So du dx is going to be 1/4. So du is 4 dx. So that right there, though, I think is enough because I see that the 4 is coming back there to make the 8. So I'm pretty set on that one. But that was tough. I could not look at that without, and get past B or D. But even so, like if you spend a minute and get down to 50-50, that's not bad, right? Look at it for a minute and get down to 50-50 guess. I'll take that. Again, 50%, you're living in 4 land. So I'll take 50-50s. All right. We're going to shift gears. I'll put a question or two like this on the next test or whatever, just as some filler. Maybe I'll even make it multiple choice. Or I'll give you the answer somewhere in there. Just to kind of practice that. But today we're going to start chapter 6. And here we're going to be talking about applications for integrals. So the first idea, the first thing we're going to be interested in is figuring out how do we find the area between two curves. So let's say I want to find the area S there. So if I think about that, I can take that area, which is just the integral a to b f of x dx, and I can add that to this area. What's the problem with that, though? What's that area from the blue integral going to be? Negative, right? So I shouldn't be adding it, I should be subtracting it. And then from our property of integrals, we can smash those together inside the same integral. And that's going to be my technique. So if I want the area between the two curves, I just do the function on top minus the function on bottom, and then I integrate. That feel okay? Now, what is this function, or f of x minus g of x, really talking about? If I relate this back to Riemann sums, because that's all this integral is these infinitely narrow Riemann sums, correct? Our f of x minus g of x is just the height of our triangle, or a rectangle, and delta x, or dx, in the integral is just going to be the width of that infinitely skinny rectangle. So that's all we're doing. So there's our formula. What happens if g of x is just the zero function? Yeah, it's just the integral of f of x, right? It's just the same thing as just our general area under the curve interpretation of an integral, right? Which is lovely, right? We'd like, when we make a generalization, it to fit the previous definition. So let's do an example here. Let's say we want to find the area of the region bounded above by the curve y equals e to the x, and below by the curve y equals x, and then bounded on the sides by x equals 0 and x equals 1. So that blue area there is what we're looking for. So we are going to be integrating. Our area starts at the x value 0 and ends at the x value 1. So we know we're integrating from 0 to 1, and it's going to be a dx function because we're integrating along the x-axis. The function on top is e to the x. The function on bottom is just x. Everybody's cool? How am I going to do this integral? Yeah, I can just kind of distribute it, right? What's the antiderivative of e to the x? Okay. What's the antiderivative of x? X squared over 2. And then we just evaluate from 0 to 1. So that gives me e minus 1/2 minus e to the 0 plus 0. Or just e plus a half. Since e to the 0 is 1. Oh, I'm sorry. It should be minus 3 halves. Excuse me. Thank you. No big deal, right? That was easy enough. Right? Not fundamentally different than anything we've done. The setup's a little different, but whoop-diddy-doo. So let's say we want to find the area of the region enclosed by the parabolas y equals x squared and y equals 2x minus x. So the first thing I'm going to do is sketch a graph for myself to figure out, like, okay, what's on top, what's on bottom. You can use your calculator to do that. So I can see clearly that this is the top and this is the bottom. Everybody's okay there? The one that's opening down is on top. The one that's opening up is the bottom. And then I'm going to be integrating along from 0 to 1. Now I can see that from my picture. How would I find that algebraically? How would I find those points of intersection for those two curves algebraically? Well, I just set the two functions equal to each other and solve for x. Right? So just like algebra 2 question. So we're integrating then from 0 to 1, 2x minus x squared is our top function, then minus x squared is our bottom. Here I'll do a little bit of light cleanup before starting doing any integration, just to make the substitution at the end a little bit easier. So really I'm going to be integrating 2 times the integral from 0 to 1, x minus x squared. So my integral for, or the antiderivative for x, we said was x squared over 2. What's the antiderivative for x squared? X cubed over 3. And we're evaluating from 0 to 1. So I have 2 times 1/2 minus 1/3 minus 0 plus 0. Let's see, 1/2, that's 3/6 minus 2/6, so that's 1/6 times 2 is 1/3, I think. Yeah, I did.
Oh.
1/6 times 2 is the 1/3. So 3/6 minus 2/6 is 1/6, then times 2 is the 1/3. Mackenzie. Right. If from the picture we had that, I was saying, how would you get it without the picture?
Okay.
Right. So if you're given the picture, that's fine. But if you're not given the picture, what do you do? Right? So see our next question, where we're not given, 0 we can surmise from the picture, but we're not given the other endpoint, right? What is that value going to be? Well, we can see that this is the top, this is the bottom, but we're going to have to now look at this algebra problem. That looks like it's going to take me probably a half an hour or more, and I'm not convinced I could even do it by hand. because it's going to get real ugly real quick. What can I do? Calculator, yeah. So the best way to go at this would just be to type in the left-hand side and then the right-hand side and just find the intersection. Oops. Oh yeah, that's fine. And really, this is a trick whenever you have a solving problem that you're not really sure algebraically how to solve it. This trick will work. And then my window, I can pretty much guess a decent window so I can see the intersection. That's like -2. That looks like 4. And it looks like we're going -2 and then +3 maybe. So here's my function. Second trace, intersect command, enter, enter. And now the guess matters a little bit because you have more than one intersection. So I'm going to move my guess so it's pretty much on that intersection just to make sure it doesn't do something dumb and just find this one over here. So I got about 0.118, or I'm sorry, 1.118. Woof, guys. What am I going to do with this first integral? Not with the x in the numerator. The numerator have to be 1 for cosine inverse. This is just a U sub problem. Yeah, dead on. Who whispered it back there? Mackenzie, good eye. Absolutely. So really what we have here is we're going to be integrating 1 over square root u, well, I guess put 1/2 out here, du, right? Everybody's okay with that? I'm just taking that, I'm doing a sub problem and then I'm going to write down equals up here because I don't want to do a U sub for the whole thing.
Yeah.
Because I don't have a way to substitute that stuff in. I'm just doing that one part of it, and I'll come back and do the rest of it afterwards. So what's the antiderivative for 1 over the square root of u? Nope. We're going to think about that as u to the -1/2. So it should be u to the +1/2 over +1/2, right? So this really just simplifies down to u to the 1/2. So that's going to be x squared plus 1 to the 1/2. I'm going to go ahead and do the substitution back in because I'm just going to do this all in my calculator when it comes time to substitute the 118 in. So like it doesn't bother me at all to just put the x back in since you know what I'm saying? Antiderivative of x to the 4th is x to the 5th over 5, and my antiderivative of x, I'm going to just do that. It's x squared over 2, and then we're going to evaluate from 0 to 0.118. Now, if I plug the 0 in, that's easy to see that I'm going to have 1, 0, 0. So I know I'm going to have the minus 1 at the end for the 0 part. Is everybody okay with that? The other part I'm going to just do on my calculator. So I'm going to have 1.18 squared plus 1 to the 0.5 minus 1.18 to the 5th divided by 5 plus 1.18 squared divided by 2. So I have 178 or 179, or about 0.79. Feel okay? Got a little uglier, right? Because you had a U sub snuck in there, but that's okay. We know how to do U sub, and it's never going away. What if we do if one curve isn't always on top of the other curve, like this? Yeah, we're just going to break this. Say that this is like C and this is D. So we do the integral from like A to C of f of x is on top here. And then from C to D, g of x is on top. And then from D to B, f of x is back on top. So we just break it up into pieces. Okay, no big deal. We can handle that. What else could you do? This is actually the same thing as the absolute, or the integral of the absolute value, f of x minus g of x dx. But how are we going to integrate an absolute value function? Just going to do that, right? So like having the absolute value as the formula, not that helpful to us, because in practical senses, what are we going to do? We're going to find out where the sign flips and just kind of like, you know, do exactly what our intuition would have said for us to do. All right. So let's go down and take a look at another example. Here we want to find the area of the region bounded by the curves y equals sine x and y equals cos x on the interval from 0 to pi over 2. So again, we gave you the picture here. Notice from 0 to pi over 4, cosine is on top. But then from pi over 4 to pi over 2, sine is on top. So that area is just going to equal the integral from 0 to pi over 4 of cosine x minus sine x dx plus the integral from pi over 4 to pi over 2. On that interval, sine is on top. So we'll do sine x minus cos x. God bless you. God bless you. Does that feel okay? What's the antiderivative for cosine? Sine. Good. And what's the antiderivative for negative sine? Cosine. Okay. Let's just go ahead and evaluate this now. What's the cosine of pi over, or sine of pi over 4? Should be able to do these in our head without having to look it up. It's a unit circle value. Root 2 over 2. What's cosine of pi over 4? Same thing, excellent. Sine of 0 is? Sine of 0 is? 0. Cosine of 0 is 1. Okay. All right. And then let's go ahead and do the antiderivatives for the other one. So sine of, or the antiderivative for sine is negative cosine. Excellent. Oh, I guess those should be minuses there, right? Dum-dum. Okay. Negative cosine. And then the antiderivative for negative cosine is negative sine. And we'll evaluate that from pi over 4 to pi over 2. So cosine of pi over 2 is 0. And then cosine, or sine of pi over 2 is 1. Okay. Cosine of pi over 4 we did already. Okay, so let's see what we have here. We have root 2 minus 1. We have another minus 1. Then we have negative root 2, but we made it negative, so it's a positive root 2. So we have 2 root 2 minus 2. Of course. All right. Last idea. What if these functions aren't written with x as the independent variable? What if y is written as the independent variable? No, man, we'll just integrate with respect to y. Right? In that case, just the height is the function on the right minus the function on the left, and then the width of our rectangle is delta y, or dy. So it's just going to be the same basic idea, just we have y's instead of x's. Which is not a big deal, because I know like the integral of f of x dx is equal to the integral of f of y dy if all I'm doing is changing the name of the variable. Who cares what it's called, x or y? Same idea. So let's do this. Find the area enclosed by the line, y equals x minus 1, and the parabola, y equals 2x squared plus 6. Notice I didn't give you a picture here because I want to talk about how we go about getting a picture out of something like this. Because when everything is x is an independent variable, I trust that most of us can get a decent picture out of that between our calculator and our brains. What do I do with this, where I can't type in y squared equals 2x plus 6 into my calculator? Okay, so Blake says we can square root both sides. That's fine. So what do I get? So the square root of y squared is just y, right? What do I write on the right-hand side? Okay, everyone agree with that? You shouldn't.
Is it because X can be a negative?
Nope.
Oh,
Plus or minus. Yes. Good catch, Mackenzie. All right. Who remembers what a square root function will look like? It's like half a parabola, right? Okay. Where's that square root function going to begin? When you have 0 underneath the radical. What value of x is going to give us a 0 underneath the radical? -3. Everybody agree with that? Okay. What's going to be the next value of x that you suppose Mr. Kulik's going to mess with? If x is 1, what am I taking the square root of? 8, right? Everybody agree? I'll pass on that. If x is 2, what am I taking the square root of? 10. Pass. If x is 3, pass. X is 4, pass. If x is 5, bingo, I like that one. Yeah.
Oh.
So at x is 5, I get 4 and -4. So that's probably enough for me to get a decent picture of what that parabola is doing, right? Everybody feel good on that? Okay. To plot the line y equals x minus 1, how many points do I need? Just 2, right? Any 2 in particular you like? I like x and y intercepts, so how about 0, -1, and 1, 0? So the region we're looking for is this one. What's going to be, so what I'm going to look for then are the 2 points of intersection. How do I find those points of intersection? Well, not quite, because they're not both equal to y. So I'm going to plug that stuff in. So it's going to be like a substitution. And then to solve this, I'm going to FOIL this out. Move everything onto one side. I say, hey, look at that. That's good news. That factors. Oops. What's the problem here, though? If I try to integrate with respect to x, what's my problem? If I start at x equals -1, that's not right. Oh, what do I want here? So we're going to integrate with respect to y's, which is fine. Which function is on the right? Y equals x minus 1, or really, y plus 1 is equal to x. Or x equals y squared minus 6 over 2. And that's what we're going to be integrating. Does integrating y's change versus integrating x's? No, man, it's the same idea. We're going to stop here because it looks like I'm out of time from the sound of things. Homework problems are up there. Feel free to start. Good job today. I love the participation. Hopefully you guys felt that this was productive. I like talking about the test questions and like how to hack those. That's kind of fun. We'll see you guys on Friday. Have a good day.